let's continue then. So with probably approximately correct learning or packed learning, we have a couple of goals. So in this category of learning, we want that the hypothesis should be approximately correct, so it should be not making too many errors, okay? And so the error probability should be bound by some value. So the error should not be greater than a value. And we also want to have, with high confidence, that the hypothesis is correct most of the time. That means that the hypothesis should be probably correct by a specified probability. Okay, so let's put this into numbers and like a mathematical framework. So given the target class C and examples x drawn from an unknown distribution P of x, and this should be large values, I guess, we want to find a number of samples, or we want to find the number of samples that we need, so that such that with probability of at least 1 minus delta, the hypothesis H has an error of at most epsilon for arbitrary deltas and epsilons, okay? So this part here is this, and the epsilon part is this, okay? And this can be written as such, so the probability of, like this is the difference between the actual class region and the hypothesis class region is smaller than epsilon, greater, and this probability should be greater than 1 minus delta. And delta is bounded by a half, and epsilon is greater than or greater or equal 0, of course, because like we cannot make negative errors. Okay. So let's look at this. So if you remember, S was the most specific hypothesis. That was like the one that goes around here. And with a probability of epsilon, a sample falls in the strip that should be, so probability of a possible sample to fall in one of the stripes should be at max epsilon. So this is one of the stripes, this is another stripe, this is another stripe, this is another stripe. So if this probability for a sample that we haven't seen yet, that falls in here, should not be greater than epsilon in any of these 4 stripes. So each stripe should have like a boundary of epsilon divided by 4, so because we have 4 stripes, right? And the probability that the drawn sample misses the strip is 1 minus epsilon divided by 4. So the probability that n samples that are independently drawn miss all 4 stripes is 4 times 1 minus epsilon divided by 4 to the power of n, which should be at most delta. So that we make an error means that the sample falls into this area, so we want to have this to be, this needs to be smaller than epsilon. So we have 4 stripes there, and this is the actual class here, right? And so, but our hypothesis is much more narrow. So we don't want observations to fall in here, because then we might make a mistake, right? Because we will say it's not a family car, but it actually is one, okay? So, and we can say, okay, we don't want it to fall in any of the sides of these of the hypothesis. So if we like divide it by 4, and then we say, okay, but then like with 1 minus epsilon divided by 4, we make that the sample misses the strip, so that's like around here or in here, right? And so I need this many samples to be, and if they all miss the strip n times, so like if I have this probability that I miss it once, then I have this probability that I miss it n times, because they're independent from each other. and then I can multiply it by 4 because then they miss all 4 strips, and this should be at most delta, so this goes in here, okay? So then we have that this probability should be smaller or equal than delta, and then with this inequality here, we can assume that we need n greater or equal 4 divided by epsilon log of 4 delta as our number of samples. So if we want to have our error super small, which means this value is really, really small, it's not, or it could be 0, but let's say it's very, very small, then we need a very large n, okay? And the same for delta, that if delta is really, really small, then we need a very large n. That means we need to get a lot of information about our distribution to be able to find a solution that is very, very correct, okay? In this example, of course, it's not that many that we need because the problem is quite easy. But we want to have a good approximation, and this is kind of like the framework that we can use. And there's a lot of probably approximately correct algorithms that can be proven, and so this is kind of like an upper boundary of giving you a hint of how big should my my data set or my training set be if I want to make a certain type of error, right? So if you get a task and say like, okay, you can make at most 10% errors, you can use this framework to identify how many samples you will need to be about as accurate as this, okay? So it's kind of, before we had the idea of the Watnick-Scherer-Menkes dimension, say like, what kind of algorithm should I choose, and what is the expressiveness of the algorithm, how good can they, or like how many data points can they shatter, and in this case we want to know how many data points I need to find a solution that is good, okay? That's also, again, an upper boundary. Alright, or in this case it's actually a lower boundary. But most of the time we deal with real-world problems, and in real-world problems we don't have these very predefined and like accurate closed classes or target classes. We always, or most of the time, have noise in our data. So we might have made a wrong observation here. So this is actually, like in this, the engine power is actually much lower than our observation, but the probe that we used to assess the engine power was wrong. It didn't work properly. It overestimated the amount of engine power. In this case, we just labeled it wrong. Somebody gave us a wrong information and said, no, this is a negative example. It's not a family car. This is actually, I have another opinion. It's not a family car. Okay, so if you compare hypothesis 1 that makes this and this error, right? Because this falls into the not the family car class, and this falls into the family car class, even though they are labeled that way. So this one is imperfect. It does make mistakes. H2 doesn't make mistakes, but it is a lot more specific, right? So you have like this crazy curve that like learns, no, this thing here is actually, while it's close to the points that are of a different class, it's actually not from that class, so I need to learn a boundary like this. So this is super specific, right? But I would not, like if I asked you, like explain me hypothesis 2, like tell me what it is, what does it say, right? So like, I would have to explain every single tangent here and say like, no, it's not here, but it's there and stuff. So it's very, very difficult to explain what's going on. But it's very easy to explain what H1 does, right? So we have 4 thresholds that we need to know about. So this is a common problem in machine learning, that a lot of times people learn very, very complex models for actually simple problems. And if you do that, you might make very, very small errors, but it's very hard to explain what's going on or what's happening. So sometimes we want simpler models, even though they make mistakes, but I can at least explain what's going on. Okay? So there's like a trade-off here. And I'm kind of alluding towards overfitting, underfitting already. And we're going to get to this. So sometimes finding a hypothesis using simple hypothesis class with 0 empirical error is infeasible due to noise, so different types of errors. And sources of noise might be faulty sensors, faulty experts, or observed variables that might look like noise. So they just, we throw them out or we don't like them. And solution might be more complex, from a more complex hypothesis class. But the question is, do we really want that? So we can always find a perfectly fitting hypothesis too, but it might be better to stick with H1, and there are some reasons. So I already explained that it is easy to check if a sample that I observe, so like this sample here, it's very easy to check if it's inside the box or outside the box, but it's harder to check if it's inside this weird thing or outside this weird thing, right? It is easier to explain, so I can tell you, okay, this is the exact price range, this is the exact engine power range that you need for a family car, so I can explain it very clearly. And the simple model has less parameters to learn, so here we need to learn all these kind of parameters. And if I remove a training point, like this guy here, I remove that, or I remove this one, this hypothesis class doesn't change a lot, but the hypothesis class, or the hypothesis 2 might change quite a bit. So if I throw a dot in here, so it might learn something like this, right? So it might change a lot, but again, all of these points could be associated with noise. So there could be noise in each of those points for different and various reasons. So what you can say in the general rule of thumb is that very simple models that use little number of parameters are much more robust against noise than models that are taking every single possible parameter into account, okay? And so if we find 2 models that have about the same empirical error, we should kind of, like as a rule of thumb, always use the one that uses similar, less parameters, okay? So if these, like if the H2 would make like maybe 1 or 2 more errors, or 1 error in total, we should always go with H1, right? In this case, we don't know. I mean, like, it could be that the class actually looks like H2, but we know that it's not the case. But so it's kind of like a trade-off between how accurate do I want to approximate it and how susceptible do I want to be, or how little susceptible do I want to be towards errors, okay? Towards noise and other observations. So that kind of leads us to a very common problem. It's kind of like the bias-variance trade-off. So if I conduct a machine learning experiment on the same data set many times, right? And my result is always about exactly the same. We have one of 2 possible outputs, or like one of 2 possible cases. Either I have low variance and a low bias, or I have low variance and high bias, right? So I might learn about the same structure every single time, but this, like, I'm always off by a little bit. or I might learn it perfectly. So this is the ideal case here, right? Of course. This is a case that we can also kind of sometimes deal with if we understand that there's a bias, so we could, for example, just subtract it, right? But that's not always the case. If I conduct my machine learning experiment a number of times and I end up at different kind of spots all the time, I could have a high variance problem with a low bias, where like I live somewhere close by the ideal target, but I'm not biased, but there is some variance in there, versus a case where I have a lot of variance and a bias, right? So this is kind of like the issue. And the problem really is that we can most of the time not optimize for both variance and bias. Because if we reduce the bias, we often increase the variance, and if we reduce the variance, we often increase the bias. Okay, so that's kind of like one of the issues that we face a lot of times in our life. So these are kind of the common cases. This is the ideal case, and this is the one case where you should run away. So yeah, and we want to minimize both of them at the same time. And this kind of looks like this. So often if I reduce the bias, I increase the variance, right? And like the optimum is somewhere in the middle, oftentimes. We're going to come back to this a couple of times during the lecture. Models that help us find an optimum here, or like we're going to see some experiments where we see, okay, this is actually approximating it quite nicely, but the variance is still low and stuff like that. So as a summary for that, so unfortunately it's not always possible to minimize both variance and bias at the same time. In general, bias is reduced if we make the learning more complex. So if we have many parameters, we can learn very complex functions that split the classes. So that is reducing the bias. However, complex models become more intolerant towards variance and reduce, like so the noise has a large impact on them, and this is kind of the core for the problem that alludes to overfitting, underfitting. Also, we got a slide for just summarizing Occam's razor. This is something that happens, like this is talked about often in machine learning. So if we assume that there are actually mislabeled samples in our data, then we can assume that if we find something that is similarly good and that's simple, we always should take the simple one rather than the complex one, because the simple solution is less susceptible to noise. If we know that everything is perfect in our data set, and we have a huge number of samples, we should probably take a very complex model to minimize it, but that in real life is most of the time never the case. So for example, one of the examples, or like one of the things that I work on, is depression classification or depression screening with veterans and people from Craigslist and whatnot. And so we bring them in, we ask them with a questionnaire, like they have to fill that in, say like, are you depressed? You know, this is a standardized questionnaire. And we know for a fact that people lie. So we had people come in and say like, oh, do I have to fill this in as depressed? Like asking the person conducting the study is like, no, you don't have to lie. Like, oh, but the advertisement asks for depressed people. It's like, yeah, but we want your honest response, not a fake response. So of course we exclude those people. But it's almost never possible to find noise-free data. It's like almost impossible. I would say it's impossible, but anyways. Yeah, so if we know that there is noise, a simpler solution is much more likely to generalize well. And it is very easy to, as you can see now, it's very easy to optimize everything on a small training set, but it's not very easy to come up with a classifier that is generalizing well over unseen data that the problem has never seen. Like you have never seen other data sets or data points in the data set, but that's very hard to do, okay? Just very briefly, if we don't have just two classes, because this is going to be a little part of what we're going to do in the homework. So if we don't have two classes, but we have three classes, what options do we have? So there are two kind of main options that we have. So on the one hand side, we can say we do a one versus all classification. So we say, I want family cars versus other cars. And I'm not saying luxury or sports cars, just other cars. And I can say, I want luxury versus other cars, or I want sports cars versus other cars. That's one versus all. But then I can also do one versus one. So I can say family versus luxury and family versus sports. And the same for these. Okay. So we are creating different number of classifications. So we have multiple classes. Goal is to find a boundary that separates one class from all the others. Multi-class problems can be reduced to k two-class problems, so one versus rest or one versus all. Alternatively, you can reduce it to k times k minus 1 half many one versus one problems. That's just like a rule of thumb, okay? And our hypothesis will look a little different. They will look like this. So we have k hypothesis now. So hi of x is 1 if x is element of ci and 0 if it's not. Okay. And then our empirical error looks a little bit different as well. Now we sum up over all the data points and all the classes, or all the k two-class problems, how many times we make an error, okay? So that's kind of like just a little change to what's going on. Okay, questions to this? Alright, so now we get to a little less theory, more practical exercise. So we are interested, and this is really important, because what we want to do is we want to conduct machine learning experiments, right? And to machine learning experiments, there are several steps to it. And we're going to go through these steps, and I'm going to repeat this probably multiple times because this is something you really need to hammer home. So, in general, we can split it up into training, validation, and test, okay? And in this case, we're separating not, so in this case, these are not phases, but data sets, okay? So we have a training set, a validation set, and a test set. So what do we do with the training set? We train our model, we adapt the model hidden variables, and we want to identify like the empirical error on our training set. So we optimize for that. With the validation set, what do we do with this? Exactly. So we want to see how well is a one-layer neural network working, how is a two-layer one working, do I need a line, do I need rectangles, what should be the shape of the ellipse, the radial basis function or whatever. So that's kind of like the validation. And the validation can be also iterative, so we can do this on many different configurations. So I don't know, I want to compare neural networks with support vector machines and rectangles. That's my three classes. They have many different parameters and I need to validate for all of them. And then after I've done this, I take the best one and then I do the test with it, okay? And the test the test set until this point, which is the very, very last point, I've never seen, never touched, never done anything with. Okay, so that's very important. So training set is used to build and construct or train the classifier, thresholds of rectangles, etc. Validation set, which algorithm hypothesis space works best, what should the parameters be. Okay? Neural network versus support vector machines versus decision trees, etc. Number of layers and size of layers of the neural network, etc. And then test set, estimate future error rate or generalization capabilities. And that's what we report. Okay? This is all methods, and then in a paper we would report this and exactly how we conducted the methods, right? So that's what we do. And this never used to optimize performance. And never report just the best run if we do multiple validations, etc. Always averages. So there are different methods for validation. So one would be, and in this case we split our data only in the training and test set. So it's cross-validation. So we can take this out and never touch until we're done with the whole thing. So we have like two main goals: reduce the training error on the training set, and then reduce future error and estimate error as close as possible on a large testing set. So that's the ideal case. And training and test set never overlap, okay? And in this case, we can also do multiple training and multiple test evaluations. So the test is like a different part of the training set. We can do that too. And this is still kind of like all validation. And ideally, we would have something out here that we never touch, okay? There's another case for leave one out. It's a special case where the data held out for testing is only a single observation, pros and cons. So like, let's say if we have these 15 points for family cars and not family cars, we take 14 of those samples and train something and then test on the last one. So that's kind of like a bit, and we rotate this through. There are pros and cons for this. It learns the best possible classifier, but it probably overestimates it. It's very highly computationally expensive, and the classes they're not balanced. That's one issue too. But this works really well on very small data sets. So if you have only 100 observations, something like this can work, but it's not ideal. You always want big data for both training, validation, and test. Yeah, so other questions? So we're gonna have like there's in the Matlab environment, we have a couple of functions that help us do these cross validations and partitionings. We're gonna come to that after this hour is over. Okay, so let's talk about some evaluation measures. So how to measure if a system is doing well. So we had like the error metrics before, right? So that was empirical error, like how many times do I make a mistake, right? So that's a way to do it. The opposite of that is like how many times is the system doing something right? So that's called accuracy. But the unfortunate thing is that this is not always working out well. And in particular, it doesn't work well if we have a certain type of problem. And it doesn't work well if we have a problem that's, for example, very imbalanced, where I have a lot of negative examples and only like a few positive examples, right? So our hypothesis A makes a few errors, right? These are correct, but these are wrong. This hypothesis B makes less mistakes, so it only makes these two mistakes. But really, it didn't learn anything. It just learned that there are no positive examples. Yeah? So, accuracy or empirical error are not always good. They don't work, for example, on very skewed data sets. Okay? So which one is a preferable? Well, in this case, none is really preferable, but A at least learns a little bit that there's something going on. So we are going to discuss measures that are not as susceptible to this kind of problem. So we can report errors also in some sort of like, this is called a confusion matrix, where in this case, like the rows here are the test outcomes, and the columns are the conditions, the truth, and this is the prediction. So this is 1, 1, 0, 0. And so if my hypothesis output is 1 and the true output for that sample was 1, I count a true positive. Otherwise, if both are 0, I count a true negative. And if I make a mistake and I say 0, but it was a 1, I have a false negative, which is like a miss. And if I say 1, but it was actually 0, I make a false positive, which is called a false alarm, right? So false alarm or misses. And we can also put this into this nice diagram as well. So these are all the possible observations in the rectangle. All of them that are outside of these things are called the true negatives. These are the red ones. Out of all the observations are the real positives. So these are outside of the hypothesis. So this is the false negatives. These are the true positives, and these are the false positives. Okay? And so if we use these, we can now define classification error, which is the false positive plus false negative divided by true positive plus true negative, etc. Accuracy is the opposite, so we take the true positives and the true negatives like that, and divide it by all of them. And so these are still very skewed in the case of like a very unbalanced class distribution. Okay, so predict whether an earthquake is about to happen happens very rarely, and good accuracy if you predict always no, right? So if the weather or if the seismology department always says no, there's not going to be an earthquake, then they are most of the time correct, right? But that's not really helping. So, in fact, one solution to this is if we say, hey, but false negatives are very, very much more costly than false positives, right? So if I say, hey, there's gonna be an earthquake, but don't freak out, just sit underneath the table, and it doesn't happen, fine. But if we don't say anything and it's going to be really strong earthquake and like a lot of people get hurt, that's not good. Okay, so we can change the weight of an error. Okay, so that's one option. But there are also other ideas that we can do. So one is, so we can measure the false alarm rate, the percentage of negative classified as positive, the miss rate, the positive classified as negative, recall, and this is going to be important. So recall is the true positives out of all my true positives plus the false negatives. So this red part is the true, like the actual positive samples, right? I want to have this as large as possible and this as small as possible. So like if this is close to 1, we have like the true positives fill out almost everything, okay? And so that's one of the things that we want. And then for precision is the true positives divided by true positives plus false positives. So if this is very large, then this is very small. Okay, so if I move this ellipse down to here, then we have a very large true positive, but a very small false positive part. And we want this to be 1, 2. Okay? So we have recall, which is, can I find all my true positives? And precision, can I find only the true positives and don't like dilute it with too many false positives? Then I have found a really good solution. And these need to be reported in pairs. So either you report precision plus recall or miss rate plus false alarm rate. Okay? But there's one cool measure that's called the F1 measure, which uses both recall and precision, and because it weights them about the same strength or the same gives them both the same weight. So like you want high precision and high recall, and this is a good measure. If you have the problem that like you want you're more afraid of false negatives, then you can increase, like you can create something like a cost measure where this could be a weight that you could provide something. Okay, so that's an option there. Cool. And then this is kind of like called a utility, and this is called cost. Questions? We're going to revisit this in a real-world example in a second. So yeah, let's try to go into a real-world example. So as you might know, I'm working on behavior understanding and recognizing nonverbal behaviors and trying to understand how they relate to disorders like depression, PTSD, or distress, or social stuff like engagement, dominance, or apathy, as well as affect like frustration, agreement, or anger. We've had this last week where we talked about can we detect depression or PTSD. And so one example that I showed was like a support vector machine or a classifier as a classifier, and this is a widest margin classifier as we talked about today. And so these are the measures that I provided in my papers. It was like there was an accuracy measure, but because the classes are not equally distributed, I also provided an F1 for the positive class as well as an F1 for the negative class for depression as well as PTSD. But this is the actual example, and we listened to that last week. I think I have to switch that on again. Okay. It was already on, I guess. So let's listen to the back channels again.
Oh, okay. Oh, okay. Okay. Yeah.
And the second one. So here we were interested in the voice quality, and I mentioned that the second part of the back channels was used in an interview when the person was interviewing suicidal adolescents. And so I was saying that the tone of voice is an important, powerful aspect of human communication. I'm going to talk a little bit more about this. So with voice quality, or the tone of voice, we refer to the timbre or the coloring of the voice, not like the goodness or the like the quality in the sense of like fidelity. It's timbre or coloring, and it's an inherent there's an inherent aspect, so men usually have a more tense voice or like a deeper voice, you can hear that, versus like, you know, kids or female speakers. But there's also a communicative aspect to it, so I can like dynamically shift my voice quality. And like it has different types of meanings, and you can like you can infer like an attitude or like a mood, an affective state. You can like understand social factors, like you talk to a subordinate in a different way, or like a person that's much younger than you, you talk differently, and so on. In Finnish, people use voice quality changes as like turn management. So if I change my voice quality in a certain way, you know that next it's your turn to speak. And these voice quality changes are in effect very strongly shaped by the glottal flow or the glottal pulse shape. And so this is like a sagittal cut from like a face, and then here these are the vocal folds. These are like they were vibrating like this. So this is the frequency that they vibrate in is the fundamental peak frequency, or called pitch sometimes. And the dynamic of how this is vibrating, that defines this shape. So like the glottal, so in this case, we start here, so the vocal folds are closed. Now we're opening the vocal folds, so they're opening like this, and then they close again, but they're not a machine, so they close imperfectly. They close too hard, and they go like, they hit, which is this part here, and then they relax and go into this state here. And depending on like how tense these two vocal folds are, they like shape this differently. So this could be sharper, this could be like a very straight down line here, and then so the shape could change, and it could change like in a way like this. So these are a couple of different shapes that we can see. And then on the extreme parts, we have breathy voices. Everybody hear that? So or this one.
Learning to speak well is an important and fruitful task.
Modal voices.
Where were you while we were away?
Learning to speak well is an important and fruitful task.
And then tense voices.
Where were you while we were away?
Learning to speak well is an important and fruitful task.
So you can see there's different types of like, it has different qualities for men and female, so there's different ranges. And so we conducted an experiment and tried to classify for a bunch of different speakers these like different types of voice qualities, from breathy, modal to tense. And so conducted a tenfold cross-validation with a leave one speaker out setting, a testing set. We have baseline classifiers, standard SVMs, naive Bayes. We utilize our new method, the fuzzy input, fuzzy output support vector machine. Don't need to know what that is yet. Maybe we'll talk about this, but so we could show that our error percentage was significantly lower than the standard approaches in the cross-validation, as well as our leave one out test. And this is how the confusion matrices looked like. So in this case, these are our observations, these are the ground truths. So like you see that when we predict breathy, most of the time they are breathy. If we predict modal, most of the time they are modal. And if we predict that tense, they are most of the time tense as well. So this was one of the ways that we reported our results. And I think if you don't have any questions, we can stop it at this point and talk a little bit more about Matlab in about 10 minutes. Questions? We're going to revisit this topic, so like from now on we're going to bring like a summary of the last class at the first 20 minutes of the next course, and we're gonna kind of walk through this, and then you have to like the ability or the chance to let this settle for like come up with some questions next week and ask them then, or like send an email, put it on the discussion board if you have something. Okay. All right. So we're gonna walk through a little bit of the Matlab classification possibilities, opportunities, and then talk about some, how we do functions and stuff like that. Oh, I should probably show the assignment real quick. Basically, there are more detailed instructions online, but we have another paper that we should read. It's called A Few Useful Things to Know About Machine Learning. I think that's kind of an interesting one because it talks about like overfitting, Occam's razor, and stuff like that. It's very high level. Everything is always like a paragraph or two. So very condensed, just like nice to get an overview of like what the problems are in machine learning. And then we conduct a machine learning experiment using Matlab functions. So that's not going to be very hard. Okay, so 10-minute break and then we'll continue.